At the time of last lecture, we have discussed the applications of finite element method, concept of finite element method, use of finite element method. Next, and we have discussed the three different methods of analysis, that is analytical method, numerical method, and experimental method. We have seen the merits and demerits of these three different methods. Okay, and these are the four numerical methods. One is finite element method, boundary element method, finite volume method, finite difference method. Okay, our concern is to this finite element method. Okay, now we have studied finite, finite difference method in first year. Also, we have discussed the general applicability of the numerical methods. That is, I have shown by three different disciplines. That is heat transfer equation, structural equation, and fluid flow equations. That is, if you observe the differential equations, these three differential equations are same. Okay. Now, when we write code for one equation, for solving one equation, that same code can be used for other equations. Next, we have started this one. Am I right? We have started this one. Okay. And out of this, we have, or I have explained first point. Akshay Patil. Akshay Patil, can you
Yes,
hear
sir.
me?
Yes, sir.
Can you
Yes, sir.
speak on this first point? Already I have explained it. You speak
Yes,
just
sir.
1 minute.
FD.
FDM.
Yes, sir. It is, sir, in FDM, divide domain into grid-like structure means, sir, we have to convert the given component into structure like connection points and parts, sir. Means
Yes.
we have to show the grid at the point of connection, sir, and we have
Grid
to
at the
form
point
the
of,
structure, sir.
yeah. And finite element method.
Sir, we have to divide the given component in a different parts, and we have to show the connections by element points.
Element point.
Yes,
Now
sir.
here I will explain this once again, because this is very important thing. If we have domain like this, now half part of this domain I will show you finite difference method. Here in finite difference method, what we are using? We are using the grid-like structure. Grid-like structure means it is a structured grid, we can say. Structured grid means here, just minute. Structured grid means here the lines of this grid structure, or these boundary lines of this structured grid, are perpendicular to each other, each other. Therefore, you will get this type of grid structure. This type of grid structure means, if you observe this one, you will get this type of, you see this here, here you will get this grid structure. Okay, grid structure like a grid, that means there is a perfect rectangle when we draw these lines. Okay, and these points here, these points are known as the grid points. These connecting points are known as the grid points. Okay, do you agree with this? Now, because of this, what happens? What happens? Here, if you use this method for curved boundaries, the portion at this type of locations, portion at this type of locations, okay, portion at this type of locations, it will be missed from the grid. That means complete geometry is not captured by this grid structure. Complete geometry of this domain is not captured by this grid-like structure. Okay. Now, a reverse or opposite to this is a finite element method. Now, here I will draw the finite element method grid structure. See, here in finite element method, we can use any arbitrary shape of the element. That is, we can use rectangular shape, we can use triangular shape. Okay. like this. You see this one, any arbitrary shape of the element. Okay, now what is advantage of this? See here, when we use any arbitrary shape like this is the meshing we can say, or this is the discretization we can say. Because of this, what happens, we can capture the maximum part of the domain, maximum part of the domain or maximum part of the geometry. See here, where what we are doing this in discretization, we are approximating the geometry, approximating the geometry. Now when we approximate the geometry by this grid like structure only, then there may be chances of the big error or high error in case of finite difference method. But in case of finite element method, we can capture the more part of the geometry as compared to the finite element method. So this finite element, sorry, as compared to the finite difference method. So this finite element method is very good for any irregular shapes. Okay, now here you can see here we are dividing the domain into grid like structure, and connecting points are grid points. Here we are dividing the domain into elements, and connecting points are nodes. Okay, now see here, this and these two are related to each other. This difference and this difference, these two differences are related to each other. Now why this related to each other? Because here, if we use grid like structure, we cannot capture the irregular geometry or curved boundaries. If we use elements and nodes, that means any arbitrary shaped elements, then we can capture the irregular boundaries of the geometry or curved boundaries of the geometry. Okay, now next, here differential equation is replaced by finite difference using Taylor series. Finite difference by using Taylor series. Already you have studied the Taylor series. Okay, now I will show you how it is done in finite difference method and finite element method. And one more thing here, I will not explain this one. Solution to the differential equation is assumed in the form of simple polynomial. You will get when we discuss when we apply the finite element method for actual problem. But you have studied this one. Here differential equation is replaced by, you see this one. See, this is the problem under the thermal or heat transfer problem. This is a heat transfer problem. Our aim is to find the temperature distribution over this domain. Now this is the differential equation. Now these are the Taylor series. This is the Taylor series. This is also Taylor series. All of you know the Taylor series. Okay. So here it is just for understanding of you. Here this is y at x plus h. That means if we want to calculate the T is the temperature at x plus h. When we divide this domain into grid like structure, these are the grid points. You can see here. Here it is a one-dimensional domain. Here this is the first grid point, this is the second grid point, this is the third grid point, this is the fourth grid point, and distance between these grid points is h. Okay, now if we want to calculate T at x plus h, if we assume this is a x, and if we want to calculate the T at x plus h, okay, we have to write the Taylor series, okay. Now see here, this is a forward Taylor series, this is a backward Taylor series, and when we add these two, this term will be cancelled, okay. Now you will get y at x plus h, that is T at x plus h, T at x minus h, equal to 2tx and h square d2y by dx square or d2t by dx square. Now same thing I have done here. Here this is known as a finite difference. In finite difference method, differential equation or derivative is replaced by the finite difference. You have to remember this. Okay. Not necessary to go in detail for this, because it is a subject related to the finite element method, and we will go in detail for finite element method. Now see here, in finite difference method, differential equation is replaced by finite difference using Taylor series. You have to remember only this statement. Okay. Now in case of finite element method, solution to the differential equation is assumed in the form of in the form of solution to the differential equation is assumed in the form of simple polynomial. Simple polynomial. Okay. Now, how this is assumed in the form of simple polynomial? What are the rules for deciding that polynomial? You have one unit on this, that is interpolation models. That unit, it is a second unit, and in that we will discuss what are the interpolation polynomials, what is the purpose of interpolation polynomial, how to select the interpolation polynomials for different elements. That everything we will discuss related to this difference. Now here you have to remember only this statement. Okay, details of this statement we will discuss in the second unit. Okay, here solution is obtained at grid points only. Solution is obtained at the grid points and results are not interpolated. What is meaning of this? I will tell you. What is meaning of this? I will tell you. You see this one here. Okay, if I solve this problem, if I solve this grid structure, suppose the grid structure. Okay. Now, when we solve this by finite difference method, what we will get? If it is a thermal problem, we will get the temperature at these grid points only. At these grid points only. Here, 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 here. If it is a thermal problem, you will get the temperature in terms of the numbers, not in terms of the equations. And that numbers are associated with these grid points. Okay, you will get the temperatures at these grid points, and if you want the temperature at any intermediate point on this, that means if I want the temperature at this location, that is not possible by finite difference method. Okay, that is not possible by finite difference method. Okay, and in finite element method, if we use same domain, and if we discretize this domain by using elements and nodes, then what we will get? We will get the temperature at node points. Here, here, here. We will get the temperature at these node points. Okay, and it is possible to interpolate this temperature at the node points at any point on the element. We can get the temperature at any point on the element. Here, first we will get the temperature at the nodes. In the finite element method, and that temperature can be interpolated over the element. And when we interpolate that temperature over the element with the help of that interpolation polynomials, okay, that will give the temperature or result at any point on the element. Have you got this? Have you got this? Have you got it? Akshay Shinde, have you got this concept?
Yes, sir.
Okay. Can I go for next?
Yes, sir.
Okay. Now see here we will get the solution at the grid points and results are not interpolated. Okay. And here solution is obtained at the nodes and results are interpolated over the elements. Now what is advantage or what is the application of this point? I will show you. See here, if you want to do the analysis of the combustion chamber, now if you discretize this combustion chamber or any combustion chamber by using grid like this one, that is by, if you want to solve the problem by finite difference method, so here you will get the temperature at some specific points, okay, that means at grid points. But if you have temperature, maximum temperature at a location other than these grid points, then that maximum temperature is not captured or cannot be captured by finite difference method. Okay. Now opposite to that, this is a finite element method. In finite element method, if you do the analysis of the combustion chamber and if you mesh it by elements and nodes, you can get the temperature. Initially you will get the temperature at the nodes, but if you have maximum temperature other than that nodes, that also we can get, that temperature also we can get by interpolation polynomials, by interpolating the results over the domain of the element. Okay. Now next one, Next one, results are already I have explained it. Now here results are not good for curved boundaries, so it requires the help of other methods. It requires the help of other methods. That means here finite difference method, it will not give the results for curved boundaries. For capturing the curved boundaries, we need other numerical methods like boundary element method or finite volume method. Okay, boundary element method or finite volume method. So here finite volume method is specific or specially used for fluid dynamics. Boundary element method is used for acoustic problems. Okay, that method requires with this finite difference method, otherwise we will not get the acceptable results for irregular geometries. Okay, now here finite element method, it has big advantage, it doesn't require any help from other methods. Okay, now this is the difference between these two methods. Now we'll go to the next. Now these are the advantages of the finite element method. You see this one. Already I have told you, that is it can handle very complex geometry. This is the heart and power of the finite element method. Okay, we can handle any complex geometry with the help of finite element method. Okay, that means if your problem is having complicated geometry, it has lot of curvatures, it has a lot of slots, then also we can use the finite element method for solving the problems related to that domain. Okay, now here it can handle the variety of engineering problems. That means we can use for structural analysis, that is the solid mechanics. We can use it for solid dynamics or dynamics problems. We can use for heat transfer problems. We can use for fluid flow problems. We can use it for electrostatic problems. Okay. Now these are the applications, and more than that also we can handle by using finite element method. Okay. Now next one, finite element method can handle complex restraints. That means intermediate structures. Intermediate structures can be solved by using finite element method. That means if boundary conditions are not well defined, that type of problems also can be handled by finite element method. Finite element method can handle the complex loading, that is nodal loads, element loads, time dependent loads. That is here this is a point load, this is a distributed load, pressure, thermal load, inertia forces, and transient problems are also can be solved by the finite element method. These are the advantages of the finite element method. Okay. Now what is a finite element method? What is finite element method? Now here finite element method, it is a numerical solution to the field problems. What are the field problems? Field problems means mathematical models related to the any field applications. Okay, means differential equations related to the field applications. That means differential equation related to the structural problem, differential equation corresponding to the thermal problem, differential equation corresponding to the fluid flow problems. That type of problems are solved by the finite element method. Okay. Now how these problems are solved? Here initially finite element method cuts the structure into several elements. Suppose this is a problem. It is going to cut the domain into several elements, that is pieces of the structures. Okay. And connecting points are known as nodes. That is these elements are connected by the nodes. These nodes are pins or drops of the glue that hold the element together. Means here initially it is not discretized, it is not converted to the elements. Okay. Now after that, in finite element method, first method is discretization, or first step is discretization, or first we are dividing that domain into number of subdomains. So here these subdomains are not separate domains. These subdomains are connected by the elements, and these subdomains are not separated when we apply the load. Okay, we agree with this, because there is a connection between these elements. These are not part of the geometry. These are just for solving the differential equations. Okay, we are not cutting the geometry into number of pieces. Actual cutting the geometry into number of pieces. What we are doing, we are dividing that into number of parts for solving the equations. Okay. This process results in the simultaneous algebraic equations. This process results in the simultaneous algebraic equations. That means when we divide this domain into number of elements and nodes, and when we solve the differential equations over these elements, we will get the system of algebraic equations. That means set of system of algebraic equations. We will get the huge number of algebraic equations. Okay, that equations we are going to solve for getting the solution at the nodes. Okay, now here I will explain this concept in the discretization. Here number of degrees of freedom over the whole domain is infinite. Okay, that infinite degrees of freedom, when we want to find, then we have to solve the infinite equations. Okay, but in case of finite element method, we are converting that infinite degrees of freedom to the finite degrees of freedom. That is the origin of the finite element method. That means infinite degrees of freedom are converted to the finite degrees of freedom, and we can get the solution for finite degrees of freedom. Infinite degrees of solution, solving the infinite degrees of freedom. That means solving the infinite equations, infinite number of equations. It is not feasible, it is not possible by any means. Okay, that we are making possible by finite element method by converting infinite degrees of freedom to the finite degrees of freedom. Okay. Now see here you will not get the clear idea, but when we start actual finite element method, we will get you will get clear idea of this one. Here you will get this subject is tough, but it is not tough. How it is not tough, I will show you. Okay. Now see here this is one slide. In this slide, what I have written, many engineering problems can be expressed in the governing equations. Governing equations means what? Differential equations and boundary conditions. That means many engineering problems are defined by these governing equations and boundary conditions. That is mathematical models and boundary conditions, differential equations and boundary conditions. That means all engineering problems you can get in this form when we write in the mathematical form. It has one differential equation and some boundary conditions. Okay. If we go for the elastic problem, already I have shown you elastic problem, equation of the elastic problem, that is d2u by dx square. Okay, it is equal to 0. That is for one-dimensional elastic problem. Already I have shown differential equation for the one-dimensional thermal problem. Already I have shown differential equation for the fluid flow problem. Okay, electrostatic equation also. It is in the form of differential equation. See here, all these engineering problems are in the form of governing equation or differential equation. Here, this is L phi plus F is equal to 0. This type of differential equation you will get. That is, I have written here just the equation. L is your differential operator. Okay, L phi means it is d phi by dx or d phi by dy or d phi by dz or d phi by dt. That means L is your differential operator. Okay, all engineering problems are expressed in the form of differential equation plus F, that is equal to 0. Okay, that means here this equation is in the form of d phi by dx. It may be higher order derivative, it may be first derivative. Okay, plus fx plus fx, it is equal to 0. That is the differential equation corresponding to that discipline. Okay, here phi is known as the field variable. Or phi is the variable which describes the behavior of the problem. Okay, field variable means what? It is the major variable which describes the behavior of the problem. In case of thermal problem, temperature is a field variable. If you get the temperature variation over the domain, you can get any property of the problem. Okay, that means temperature is a field variable in case of thermal problem. In case of elastic problem, in case of structural problem, displacement is a field variable. If you get the displacement of each and every point after the application of the load, you can get the stress, you can get the strain, so on. That is known as a field variable. Okay. Next one, there are some boundary conditions. In case of structural problem, boundary conditions are forces, reactions. Okay, These type of boundary conditions, that may be in the form of differential equation, that may be in the form of constants, okay, that may be in the form of equations, okay. Now this will complete the engineering problem. That problems are solved by the finite element method, means these differential equations with the help of these boundary conditions are solved by the finite element method, okay. Now next one next one, now see, this is the concept, fundamental concept of the finite element method. Here already I have told you, finite for finite element method we need this one, governing equation, boundary conditions, and finite element method will divide the domain into number of subdomains, okay. That means it is approximating the geometry, it is approximating the domain. When it is approximated, then that will be converted to the system of algebraic equations, set of algebraic equations, and that set of algebraic equations are written in this form, that is k into u is equal to f, okay, k into u is equal to f. Now see here, k into u is equal to f, k is your square matrix of the constants, u is your behavior or it is a field variable matrix, f is your action matrix, okay. That means under the action of this f, for this k properties, what is the behavior of the domain, it is described by the finite element method, okay, or it is calculated by the finite element method, okay. Now u is a field variable matrix, or it is a vector. Now field variable matrix for display, for structural problem it is displacement, for thermal problem it is a temperature, for fluid problem it is a velocity, okay. Now you see this one, k is your property matrix, u is behavior matrix, f is your action matrix, okay. Now I will show you. See here, our aim is to find the behavior, that means we want to find the complete behavior. For finding the complete behavior, what we have to do, we have to solve these simultaneous equations for the u by using this constant matrix and f matrix, okay. K inverse into f, that will give the behavior. Now see here, I have given here list of disciplines and corresponding property matrices. Property matrix for structural problem it is a stiffness, property matrix for thermal problem it is conductivity, and for fluid it is a viscosity, okay, and for electrostatic it is permittivity. It is not for our domain, this is also not in this content. We are going to solve these problems, that is thermal and elastic problems, okay. Now here displacement is a behavior matrix, temperature is a behavior matrix for thermal problem, force is a action matrix, and heat source is action matrix for thermal problem. Now what we are doing, we are calculating this behavior. That means under the action of this one, for these properties, what is the behavior of the problem, that we are calculating in finite element method, okay. Now Dheeraj Chavan, have you get some idea of the finite element method? Dheeraj Chavan. I think he is not here. Akshay Patil, have you got some idea of finite element method?
Yes, sir.
Okay. See here,
Yes,
those who have not got idea of finite element method, don't worry about it, because this is just a theory. From the theory you will not get the idea. When we start actual applications, you will get the clear idea of the finite element method. Don't lose your patience. My request, don't lose your patience. Keep your patience. You will get the clear idea of finite element method in the coming slides, okay. Now next one, you see here, these are the steps of the finite element method. See here, these are the steps of the finite element method. On each step, there is one separate unit. This first step is discretization. This step I am going to explain in first unit, First unit. In second step, it is a selection of interpolation of polynomial or displacement model. This step I am going to explain in the second unit. Okay. Third is derivation of elemental stiffness matrix and load vectors. This step you will get in the third, fourth unit. Okay. And some concepts related to this I am going to explain here also, in this unit also. Just I am going to explain all these steps. Okay. After that, here we are finding the stiffness matrix and load vectors for the elements that we are going to assemble in the fourth step. This step, in some books you will not get this step. That's why I have written in the red color. This step is applying the boundary conditions. That means after getting this overall equilibrium equation, that is assembled finite element equation. That assembled finite element equation is in the form of k into d is equal to f or k into u is equal to f. This is the assembled finite element equation. Okay, assembled finite element equation. After getting this assembled finite element equation, we are applying the boundary conditions, and after that this system of equations is solved for the unknown displacement or unknown temperature or for unknown field variable. Okay, and after that we are going to calculate the elemental stresses and strains in case of structural problem. In case of thermal problems, we are going to calculate the heat flow rate or heat transfer. Okay, other things we are going to calculate. What we are going to calculate, that I will explain by taking the numericals on this, and before that we have to complete the equations. We have to derive the equations for that. Now I will explain one by one. In discretization, here actual domain we are dividing into number of parts. That means we are converting the domain into elements and nodes. That process is known as a discretization. In case of software analysis, this step is known as a meshing. That is discretization of the structure. In software language, it is a meshing. Okay. Now see here, why we have to do the discretization? What are the rules for the discretization? What are the different types of elements in the discretization? Okay, that we will discuss under the special topic or subtopic, we can say, on the discretization. What are the rules for the discretization? How we will start the discretization? What are the elements we are going to select for the discretization? Okay, that we will discuss in the discretization separate content. Okay, next, selection of proper interpolation or displacement model. Your second unit, it is based on this one. That means total detailed study of this step we will discuss in the second unit. What are the interpolation polynomials? What is purpose of interpolation polynomials? Why we have to select the interpolation polynomials? How we are going to select the interpolation polynomials? What are the different interpolation polynomials for different elements, that we will discuss in the second unit. Okay. Now next one, derivation of elemental stiffness matrix. Here, how we can derive the elemental stiffness matrix? That means for single element, how we can derive this K matrix. For each element there is a K matrix. Okay, that is known as the elemental stiffness matrix. How we can derive that elemental stiffness matrix, that is stiffness matrix for individual element, that we will discuss under this step. Now next one, assembly of the elemental equations to obtain the overall equilibrium equation. That means after getting all stiffness matrices, that means stiffness matrices for all elements, we are going to assemble that all stiffness matrices. Just we are not adding that, we are going to assemble that stiffness matrices. And when we assemble the stiffness matrices, we will get global stiffness matrix, or it is a assembled stiffness matrix, or it is a overall stiffness matrix. Okay, how to do that? That also I will explain. Okay, after that we will get the overall equilibrium equation, that is stiffness matrix into displacement matrix, that equal to the force matrix. That overall equilibrium equation you will get, and after that we are applying the boundary conditions. What are the boundary conditions? You see here, this this is a fixed, means nodes connected to this support are not moving in any direction. That means displacement of these nodes is 0. That we are putting in this field variable matrix or displacement matrix. Okay, and after putting that boundary conditions, we are solving these equations. Okay, and when we solve these equations, we will get this D matrix, and this D matrix is a behavior matrix. Okay, or field variable matrix. After getting this field variable matrix, if required, we will go for the further calculations for calculation of the stresses and strains. Okay. Now these are the steps of these steps are very important steps. Everyone has to remember the sequence of these steps is also important. I will ask during my successive lectures each and every time. Okay, what are the steps and what is the sequence of the steps? Okay, these steps are very important. If you follow these steps, you will get the solution. Okay, you will get the solution. So here again you have to remember, first is discretization, second is selection of interpolation polynomial, third is the derivation of elemental stiffness matrix, fourth is assembly of the elemental stiffness matrices, and fifth is boundary conditions, then solution of unknown displacements and computation of the elemental strains and stresses. Okay, have you got this? Have you got this? Arman Attar, are you here?
Yes, sir. Yes, sir.
Can you remember these steps? See here, you will not get the complete meaning of these steps, but you have to remember just the sequence of these steps and title of these steps. Okay, Rishikesh Kumbar. Whether he is here or not.
Yes, sir, I'm here.
Can you remember these steps?
Yes, sir.
Here, don't take tension. Here you will not get the idea of the finite element method, but from next lecture you will get the idea of finite element method, because I have just told you these steps. I have not used these steps for any problem. If when I start the using of these steps for the problems for domains or different disciplines, then you will get the idea of these steps. Okay, it is very simple. Next one. Next, you see this one. These steps are same to the your software analysis step. In software analysis, what we are doing, I will show you here. Computer implementation of the finite element method. In software analysis, we need the CAD model. Okay, we are dividing the we need the geometry of the problem. Okay, that is CAD model. After that, we are dividing that CAD model into number of parts for solving the problem. That means it is a meshing, or it is a discretization in finite element method. After that, here this discretization we have to do in software also. This selection of proper interpolation polynomial, derivation of the elemental stiffness matrix, assembly of the elemental equations, that here will be taken by the software itself. Okay, that means when we divide the domain into number of parts, that means when we mesh the problem in software, in ANSYS, in HyperMesh, we are meshing the problem. When we mesh the problem, then software, depending upon our selection of the element, software will select the polynomials automatically. Then it will assemble it will calculate the stiffness matrices for each element. It will calculate the assemble the stiffness matrix. It will formulate the overall equilibrium equations. Okay, do you agree with this? Then we have to apply the boundary conditions. Software will not apply the boundary conditions. We have to apply the boundary conditions. Okay. Next, processor stage. Next, we have to give some settings in the solution. Where after giving some setting in the solution, software will solve the all system of linear equations. It may be thousands of the equations, it may be lakhs of equations. Any number of equations can be solved by the software. Okay, this is also done by the software. Then post processor, here results are in the form of numbers. That results you have to we have to analyze that results. Okay, that results, that is known as a post processor. Okay, result processing and taking the different plots, that is known as a post processing. Okay, I will show you here. See here, this CAD model is this one. CAD model is this one. Okay, this is your CAD model. Now this CAD model, what we are doing in the software, we are converting that CAD model into elements and nodes. Elements and nodes, that is known as the meshing. Here it is, we are doing the meshing. After that meshing, we are applying some boundary conditions. Okay, and we are solving that. That means software is going to solve that problem. Okay, after solving, we have to take the some plots, that is contour plots, graphical plots. Okay, this part is known as a preprocessor, and next software is going to solve the problem, that is known as a processor, and we have to check the results, that part is known as a post processor. Okay, now I will stop here. I will send one link to you. You have to use the test on this. I will send this link on WhatsApp group. Test is already started. Not sir, it will start in 2 minutes. Okay, have you got it? This test is on this lecture, on today's and yesterday's lecture, that is last lecture. Have you got it? You open your link and start the test. I think it will open at 1:05.